Today we will start the new family. In the boron family, we have studied the structure of the borons, diborane, and nidoborane also. Now we start the silicon chemistry. The atomic number of the silicon is the 14. These are the 14 group elements, and in the silicon family, they are the carbon family. In then that silicon is 14 atomic numbers. Germanium, tin, and antimony. These are the elements are in the silicon family. आवाज आता है ना?
Sir.
Next is the electronic configurations. So electronic configurations of the carbon is, we know that the 1s2 are the carbon having the 6 atomic numbers. So first two electrons are coming to the 1s2, then remaining 4 electron in the 2s2 and 2p2. In the family of the carbon family, all the elements having the valence electronic configuration of 2s2 and not 2s2, s2, ns2 and np2 is the electronic configuration. Same for the silicon also. Silicon having the 3s2, 3p2 valence electronic configurations. Germanium having the same valence electronic configuration, that is 4s2 and 4p2. S and having also same electronic on balance electronic configuration, that is a 5s2 and 5p2, and the antimony having the same electronic configuration as the family having, that is the 6s2 and 6p2. So these are the electronic configuration. Try to write this electronic configuration at your home. Okay, if you difficulty, then ask me. Next is the trend in the property trend. In that, first is the atomic radius. So atomic radius of the element of the group 14 increases to some extent with the increase in the atomic numbers. Same way, the ionization energy decreases as we go down the groups through it's not seen regularly, and this irregular trend because of the intervarying the orbital shielding. So it is responsible because of the orbitals, that is d orbitals and f orbitals involved in the um, outermost electronic configurations, and this causes the shielding and de-shielding electronic configuration. Next is the metallic and non-metallic properties. So metallic properties, non-metallic property increases on the atomic size increases. Okay, and first, second element carbon and silicons are distinctly non-metals, and the germanium is the semi-metals with some metallic properties, while the last two elements, tin and antimony, are the distinctly metallic in nature. So increasing tendency to form the metals and the 2f ions and the acidic and basic nature of these orbitals and hydrolysis also confirm that increasing metallic character from the carbon to the lead. So next is the oxidation state of and the inert pair effect. So oxidation effect is the only because of the number of electron donation by that particular atoms. So outermost valence electrons are the ns2 np2 naturally either lost 4 electron and again 4 electron acquired stable configurations, and the total ionization energy is very high for the removal of the 4 electrons. Very high amount of the energy required, hence the plus 4 oxidation state number presents. These elements do not forms minus 4 oxidation state. The only alternative left is that to share the 4 electrons with the other elements. So when they form the compound in the plus 4 oxidation state, one of the ns2 electron is excited to higher number of orbitals and the 4 half-filled orbitals. So the stability of the plus 4 state decreases and that of the plus 2 oxidation state increases from the carbon to the lead. This reduces ns electron pair taking part in the bonding and is called as inert pair effect. So already we talk about the inert pair effect because the ns s electrons is opposing to participating, and only two electrons are participated, that is the plus two oxidation state, that is called as inert pair effect. But having the four electrons and four electron donation is not possible. It required a much amount of the energy to share the four donate the four electron. That's why the silicons follow the sharing electrons pathway. So germanium and the tin form the compound in the plus 2 and plus 4 oxidation state, and Pb lead plus 2 oxidation state is oxidizing agent and more stable than the plus 4 oxidation state. Due to that effect, Pb2 plus is more stable than the Pb lead 2 plus is more stable than the lead 4 plus, and the silicon lower oxidation state increases and that of the higher oxidation state decreases in the group with increase in the atomic number from carbon to lead. So the melting and boiling points. The melting and boiling point of the element depends upon the structures. Okay, how it forms the structures and how it is a having the tendency to bear with the temperatures. So the higher melting point and boiling point of the element of group 15 decreases as we move down the groups. Carbon silicon shows the very high melting points and they have the very still diamond like strong covalent bond, because the diamond, we know that the diamond having the highest melting point required for the highest temperature required for the melting of this compound. So the having the highest carbon and the silicon, hence the carbon silicon, particularly carbon show high melting points. Next is the how the silicon is found in the nature and discuss the structure of the silicons. The silicon SiO2 or the silica is the most common compound of the silicon, and it is the most abundant compound in the earth crust, and it is the commonly decreases in the form of the ordinary sand but also exists in the quartz rock crystal chemistry. uh, and the structure of this compound is the SiO2 having the tetrahedral structure. Okay, silicon having the similar structure that of the carbons, so the showing the tetrahedral structure means the silicon attached with the four different carbon oxygen atoms and they form the tetrahedral structure. Having the infinite three-dimensional polymers and the ionic structures, and with each silicon is the link covalently with the four oxygen atoms, silicon atoms. Each silicon atom has only half shade of the each of the four oxygen atom attached with it, and the ratio of the silicon oxygen atom in the silicon molecule is as same structure is given here. In that the silicon is attached with the four different oxygen atoms, and oxygen is the bivalent atoms. So the oxygen attached with the two different silicon atoms, and silicon attached with the four different oxygen atoms. So this is about the structure of the silicon. Very simple structure. Okay. Next is the electronic configuration of the silicon is the gear 1s2, 2s2, 2p6, 3s2, 3p2. This is the most common electronic configuration of the any carbon family, that the outermost shell electronic configuration is the same, that is ns2 and p2. And having the electronic configuration of the 1s2 4 means the oxygen having the outermost electrons. Okay, so in that case oxygen required two electrons to complete is the pair. Okay, in this case the state and silicon excited state requires at the required purpose is that for the excited molecules, so we will get the same energy habit orbitals, and that same energy habit orbitals is responsible for the proper bonding with the other oxygen atoms. So this is called as SiO4 tetrahedral structures. This is the most important word regarding the silicon. Silicon SiO4 having the tetrahedral structure. Now the SiCl4, SiCl4. So SiCl4 structure, that is the silicon and the two chlorine atoms, four chlorine atoms and the two chlorine molecules from the SiCl4. In that, if you see the electronic configuration of the silicon, that is having the two electron in the outermost shells, and that is if we excited it, we will get the four vacant, four unpaired electrons, and that four unpaired electrons react with the four chlorine atoms sharing of electrically hybridized with form. Here is the structure of the SiCl having the bond length of the 109.5 degrees centigrade. So this is about the tetrahedral structure of the SiCl4. Occurrence and extraction of the germanium. Germanium is the metals and they exist on the earth crust. So the mineral containing the germanium is the argorite, and germanium does not occur in the found in the traces and occur in the small quantity in the minerals like argorites. This mineral is most found in the Germany, and the germanite 7GS GES2 in the this form this existed. It is found in the South Africa, and the germanite 4Ag2S and the Ge1SnS2. This is also exist in this form structure. It is not a freely available metals. It is existed in the earth crust in the with the another metal. So we have to perform the extraction process. Along with the extraction, purification is also required. The extraction of germanium is how extraction of metals form the its all three step, that is the reductions. So extraction of germaniums in that part is the extractions from the is the most common source of the germanium, that is the argyrolite is the generally found in the Germany, and it is the most in the most concentrations, most quantity percentages germanium exist in the argyrolite. Then the finally powdered, how to perform the extraction process is the procedure is given here. The finally powdered dry ores is fused with the Na2CO3 and the sulfur, and the fused mass is extracted with the water and the dilute H2SO4, and then filtered to remove the impurities like the As2, S2 and Sb2O3. So in this way, the first step is performed. Next step, the filtrate containing the soluble germanium salt is mixed with the excess of the HCl and saturated it with the H2S and the precipitate of the germanium as the Ge2S is obtained. And this precipitate is then washed and roasted with the nitric acid and ignited with the germanium sulfide is converted into the GeO2. Ge2S sulfur replaced by the oxygens and reduction of the GeO2 to germanium. This GeO2 is placed in the highly pure graphite crucibles and is reduced to the germanium by heating 600 to 900 degrees centigrade in the presence of the S2 gas. So if the procedure is also given the GeO2 reacted with the hydrogen gas, we will get the germaniums, okay, and GeO2 react with the two carbons, and we will get the germanium as a final product. So extraction of the from the germanite ores, powder dried heated at the second sort is that how to separate in the pure forms. The powder dried heated at the 350 degrees centigrade in the atmosphere of the chlorine to obtain the germanium as a GeCl2 along with the AsCl2, that is arsenic trichloride, S2Cl2, which are separated by the functional distillations. The GeCl2 is distilled over the 83 degrees centigrade, and distilled GeCl4 is paired with the vigorous stirring over the crush ice bath, and when the GeCl2 gets hydrolyzed GO2. The hydrated GO2 is saturated with the chlorine, distilled and hydrated with the ice. White precipitate obtained on the drying and ignitions give the GeO2, which on the reduction with the S2 or carbon gives the germanium as the final products. So this is all about the how to obtain the germanium, okay, in the form of second, and give the preparation of the borax. Borax is one of the important compound of the containing the boron, that is Na2B4O7 dot 10S2O, water of crystallization having the 10 molecule of water of crystallizations, and the boron can obtain boric acid, that is from the boric acid, that is the Na2CO3 plus 4 S3BO3 plus Na2O3 gives the Na2B4O7 plus 6S2O. So Na2B4O7 is the structure of the boron along with the having the water of crystallizations. Next method is also there for the obtaining the borax, that is the Ca2B6O11 for water of crystallization 5 molecules and the 2Na2CO3 boils with and get the 2CaCO3 calcium carbonate along with the Na2B4O7 and the Na2BO25H2O. So we will get the in six another second is procedure to obtain the uh, borax in the naturally as the chemical. Another important name of the borax and the suhagan is another name. So this is all about the boron and the boron family. Next point is that next is the zone refining method. Zone refining methods is it is the simplest form and involve the movement of reagents in the zone through the solid ingot mass, and impurities are more soluble in phase than in the solid phase. So germanium in both there is a placed in the narrow boat, and the boat is pulled through the tube furnace in which several narrow zones are created narrow portion of the ingot. So hot zone process, in this process is proceed through this molten zone and the inductive coils, then finally form the boat pulled in direction. Method different zones, materially different zones, the zone refining techniques. Liquid zone slowly passes through the solid bar and most of the impurities are rejected by the solid, and single molten zone is passed through the length in gold, impurities collected in the liquid and finally separate out by the at the very end of the ingold where last part of the molten zone finally solidified and then separated. So it is repeated number of times until the distilled state of the purification is reached. And next is the why zone refining is not effective for the purification. It is one of the important questions. The reason is that the molten silicon waste reacts and it is contaminated partially with all the substances that can be formed by making the crucible melting points of the silicon being high temperature control and the problems such as the more C1 than for the ones. So the not preferred and the cuts through the best material of the holdings silicon can barely be the used at the 142 okay 1420 degrees centigrade because of its soften and its the temperatures. This is all about this methods, and here is the method of the purification, that is the molten zone, generator, silicon coils, and the solid materials. So in this method, cylindrical silicon rod is clamped vertically at the both direction, and this diagram is most important. Okay, along with the direction, we have to descriptions of these diagrams. So as the zone refining method of the heating is the used to melt the narrow region of the vertical rods, and the surface tension of the molten silicon is sufficiently to prevent the silicon in the sufficient and prevent the silicon the falling out of the molten zone. Held is positioned by its surface tension. Then slowly pass along in go to the segregate the impurities towards the end of the rod. And this process is repeated several times till the desired purification is reached. Another method, that is a discussion of the pooling techniques for the preparation of the germanium crystal. This technique is important. Diagram is most important in this techniques. That is in the diagrams. Is a number of parts is there, which is named after the seed of the crystal, growing crystal, okay, graphite cube. So in the Zurlowski pooling techniques for the single crystal growth, as seen in the diagram, the graphite powder containing the germanium is placed in the quartz jar. The crucible is placed in the furnace, which is electrically heated. Above the furnace, there is a pooling head which holds the seed of the desired orientation made from previously prepared single crystal, and the seed is deep in the molten germanium, grows continuously on the seeds, and the seed crystal is slowly with the drawn while the rotating into the improve its appearance, and the for preparatory single crystal semiconductor symbol of the germanium. It has to be the intentionally deep with the sum of the specific impurities and to produce the material with the given conductivity. So this is all about the germanium family. Okay, we have studied some of the silicon family. Silicon family is in that there is the two metals that is the obtained from the earth crust. So the important in that how to separate out, how to extract it. It's in the pure form from the raw material form. So two three methods are given to purify and extract it in the pure form. Next is the family, the nitrogen family. So in the nitrogen family, what is the electron configuration of the nitrogen? The electronic configuration of nitrogen is the 7th. Okay, so nitrogen having bonds means the 2 electron in the first orbitals and the remaining 5 electron in the second orbitals. That is the 2s2 and 2p3. The electronic configuration in the first group of nitrogen family having the element nitrogen, arsenic, okay, phosphorus, antimony, and the bismuth. These are the elements involved in the nitrogen family. So electronic configuration having the common trains, that is the 2s to 2p3 is the common train. 2s to 2p3 is the common trend. We will find here this is common trend 2s to 2p3. If we see here 2s to 2p3 is the common trend, 2s to 2p3 s to p3 is the common trend, s2 p3 is the common trend, okay, s2 p3 is the common trend, okay. So in this way the electronic configuration of the nitrogen family is having the similarity, that is they are involved in the same group having the s2 and p3 electronic configuration at the outermost. Bismuth is also having the s2 and p3 electronic configuration, so it is clear that the group figure had ns2 and np3 valence electron in their outermost shell, and total number of outermost are the 5. The trade in physical and chemical properties. In the physical and chemical properties, we are going to study the atomic size, then the metallic character, oxidation state. These are the common properties we are studying in the all the groups, all the families. So first is atomic size and ionization energy. So with increasing, we know that with increasing the atomic number, atomic radius expected to increase from nitrogen to bismuth, and the ionization energy is also expected to decrease, and the electron positive character increase down the groups. So ionization energy of the elements are very high as compared to the group 14 elements and the metallic and the non-metallic characters. So metallic character is also depends upon the how electrons is donated by that particular items. So this is depend upon the metallic and non-metallic. Okay. So the remaining parts of this topic we will cover in the next lectures. Okay. Let's start to write the notes. नोट्स लिखना चालू किए क्या आपने?